The purpose of this review is to go through 6 really common question themes that show up almost every year on the free response portion of the Calculus AB exam. So we're going to start with the first question type, piecewise function. This has shown up 6 times in the last 10 years, all in no calculator problems. And typically, the common themes for piecewise functions are they're on no calculator questions, so questions 3, 4, 5, and 6. Piecewise functions, we've discussed this before. There's not much you can do with piecewise other than calculate slopes of lines to approximate derivatives or rates. And then we can calculate areas of the regions, which are typically geometric shapes. And that's a substitute for integration. And then we can use those values to determine function values involving expressions really for derivatives and really integration. And we can substitute those into other functions. So we're going to look at this question. It's question 4 in the 2011 exam. We have a continuous function over the interval from -4 to +3 and consists of 2 quarter circles and a line. So if you notice, they describe verbally in writing what the shapes are. That's a clue that you're going to have to use some geometry. And then they also have a function substitution. They said let g of x equal 2x plus the integral of f of t. So we know we have some integration to do, which means some areas of regions. And then we want to find function values, derivative values, and then some justifications for finding absolute maximums, points of inflections, and then average rates. So we're talking about average rates here. We're talking about derivatives. So let's take a look at part A. They want you to find the function value of g at -4. So we know that if we want to find the value at -4, we have to look at this region that we get when we go from 0 to -4. So that region from 0 to -4 starts here at x equals 0 and goes to here at x equals -4, and it contains a large quarter circle in the positive area of the graph and a smaller quarter circle in the negative region of the graph. Right now, considering this integration was set up from 0 to x, these limits are upside down. So the first thing you want to do in solving this is make sure that the limits follow that standard notation of the lower limit being smaller and the upper limit being larger. Then we can go ahead and swap out the expression for the integration. We can swap that out for geometric regions. So here's the red quarter circle, pi r squared divided by 4. It's negative because it's red, it's beneath here. And here's the blue region, pi radius squared divided by 4. It's that quarter circle up there in the positive region. And then as we simplify this, we get -8 minus, and this whole thing is 2 pi. And then we just leave the answer as that. For finding the derivative, we take a term-by-term derivative of this expression. So the derivative of 2x is just 2. The derivative of this is the derivative of the integral. So we have to recognize this as needing the plot rule to simplify, to get rid of the differentiation and the integration signs. So if we have to use a plot rule here, we check to make sure our derivative variable x matches exactly the x variable up here, and it does. We have a constant down here, 0, so we can just plop whatever value in for x we have in for t. So we go ahead and plug that in. So we have 2 plus f of x. F of x is just a function value. So if we want to evaluate this at -4, we plug in -4. So the derivative of g at -4 is 2 plus the function value of f at -4. So that's -1. So 2 plus -1 is 1. So the function value of the derivative at -4 equals 1. For part B, we need to determine the x-coordinate of the point which g has an absolute maximum on this interval. And so if we want to find the maximum of function g, that means we need to look for where this derivative is horizontal. So we're going to go ahead and set that derivative equal to 0. So the derivative of this we're going to find. The derivative is of 2x is 2. The derivative of this integral here is just the function f of x used from the plot rule, and that you can just copy down from part A. And then we set that equal to 0 and we solve that. So solving that, we get the function value is equal to -2, which is right here. Function value is the y value. So we're going to need to find this x value here. And so that's when x is 5/2. And so we have to justify as to why that's a maximum. So that's a first derivative rule, a test that we're going to have to do. So we have to look on either side of 2.5. So when x is 1, right here, f of 1 is 1. So f of x is 1, and g prime of x is, so we look at this function f of x is equal to 1 when x is equal to 1. So g prime of x is 3, so that's positive. So we have positive slope beforehand, and when x is 3, the function at 3 is -3, so 2 minus 3 is -1, which is less than 0. So we go from a positive slope to a negative slope, which if we go from a positive slope to a negative slope on those tangent lines, we have an absolute maximum. For part C, we want to list all the values for which the graph has a point of inflection. So point of inflection means that the second derivative is 0. So we're going to grab that first derivative from part A, and then we have to give a reason, and again, we keep our reasons short. So we grab our first derivative from part A, and then we differentiate that. So the derivative of 2 is 0, derivative of f of x is f prime of x. And points of inflection are where that second derivative is 0. Remember we're changing from smile to frown here. So we're changing from a frown to a smile. So we're changing from a positive second derivative to a negative second derivative, or a negative second derivative to a positive second derivative. So that so looking at that second derivative is equal to 0 tells a good part of that story. So where is the first derivative equal to 0? So we're looking for the slope of graph f. Where is the slope 0? Well, the slope is 0 right here, but that's not on the interior of the interval, that's at the end, so we can't count that. And then as we follow here, we've got some positive slope going to an undefined slope, and then some positive slope again going back to flat. So we have also 0 slope here, and this slope is constant and it's negative. So here we have 0 slope, we have positive slope over here and negative slope over here, so we must be going from a smile to a frown. So when x is equal to 0, we have a horizontal tangent, so we know the slope of the graph is 0 is our explanation as to why we know that there's a point of inflection at x equals 0. For part D, we're being asked to find the average rate of change over this interval from -4 to 3. And so when we're talking about an average rate of change, we're talking about a rate, so we want an average slope. And so since we don't have a function, we have to rely on algebra to give us our slope. So if we're talking about over this interval, then we're talking about connecting the endpoints here. And so we need to find the slope of that line. And so we're just going to rely on algebra to do that for us. So we have function value at 3 minus function value at -4 over 3 minus -4. The function value at 3 is -3. The function value at 4 is -1. So when we subtract -3 minus -1, we get -2, and 3 minus -4 on the bottom is 7. So the slope of that line, that green line, is -2/7. The mean value theorem says that somewhere along this function, we need to have a slope or a tangent line of 2 over 7. And as you can see, when we draw tangent lines on these quarter circles, they're all going to be positive. So they're never going to be parallel to this. And if we draw a tangent line on this part of the function, which would be the line itself, that's -2. That's never going to be parallel to this. So there is no point at which we can draw a parallel line, a parallel tangent line. And the reason why there isn't, and the reason why it does not contradict the mean value theorem, is because the mean value theorem has a condition that says if we're going to be able to find a tangent line with a slope of -2 over 7, we better have a differentiable function. And we don't have a differentiable function right here at x equals 0. At x equals 0, the tangent line coming off the circle is horizontal, which means the derivative is 0. And the tangent line coming off this line here is -2. And since those values don't match, we have a point here that does not have differentiability. So that means we don't necessarily contradict the mean value theorem, it's just that we can't use it because it's not valid for piecewise functions when we have these sharp points or cusps. For the next free response question type, we run into a free response question type that deals with derivative rules. So it'll ask you questions dealing with the first and the second derivatives, maybe points of inflection, or mins and maxes, those sort of questions. And a lot of times they're centered around motion concepts. And so dealing with position, velocity, and acceleration. Sometimes they're not, but a lot of times they are. So this type of question in the last 10 years has shown up 9 times. 7 of them have been no calculator questions. 2 of them have been calculator questions. So what we see here is we could see it on either part of the test, calculator or no calculator. If it is a motion type problem, typically they give you a velocity function or a table of velocity values, and then they have you differentiate for acceleration questions, and they have you integrate for position or distance traveled or those type of questions. So that typically what they have you do here: integral for position or total distance traveled, derivative for acceleration. And here are these derivative rules. Changing direction means the velocity is equal to 0, so we have that first derivative rule. Speeding up or slowing down is when the acceleration and the velocity have the same sign. So here's the second derivative rule. Total distance traveled is using the absolute value function when we integrate. Position is saying, well, I've got to integrate to find my displacement and then add in my initial position to find my final position. Acceleration means I need to do a derivative to find an acceleration at a particular point in time. And sometimes they ask you what time is it when the particle is moving a certain speed. And a lot of times this has maybe a trig application where we have something that oscillates. So you could have a couple of options for answers depending upon if it's traveling in the positive or negative direction. So let's take a look at this question. It's question 6 from 2012. And so we're going to look at this. Question 6 is a no calculator question. But what we're going to do is we're also going to show you how to solve these type of problems with a calculator, because it shows up on the calculator portion from time to time. So we'll show you kind of both parallel solutions. And this happens to be a velocity one, so this is a motion one. So let's take a look at part A. First, we'll solve this as it's intended to be solved without using a calculator. So it says, when is the particle moving to the left? So we have to associate left as negative velocity. So the first thing to do is find where the velocity is 0. And then we can test on either side to see if the velocity is positive or negative. So we have a velocity function. We set it equal to 0. So we have to think of this as, when is the cosine equal to 0? And if you think about the unit circle, right, the cosine is the x-coordinate, and it's 0 at the top and the bottom of the unit circle. So pi over 2 and 3 pi over 2. Okay, so velocity 0, that's when the particle's temporarily at rest, we might also be changing direction. So we're going to set that equal to 0. We're going to think about our unit circle. 0 is at pi over 2 for cosine, and is at 3 pi over 2. So that's the theta value. That's when the angle is pi over 2 and the angle is 3 pi over 2. The angle, though, is pi over 6 times t. So we have to set that equal to those two and solve. So when we cross multiply here, we're going to get 6 pi over 2 pi. When we cross multiply over here, we're going to get 18 pi over 2 pi. So when time, reducing this, when time is equal to 3 seconds, or when we reduce this, when time is equal to 9 seconds, we're at rest. So now we have to take a look at what that means. So thinking back to the unit circle again, we're talking about being at the top or the bottom of the unit circle. The cosine is negative in quadrants 2 and 3. That's the left-hand side of the circle. If you notice, I'm kind of sweeping across the screen here to get you to visualize the unit circle, but I'm not drawing it. So I'm trying to get you to visualize this without actually physically having to draw it, since it's not a calculator question. So we know this is negative in quadrants 2 and 3 at the negative side, or the left side of the circle. So that starts at pi over 2 and goes down to 3 pi over 2. So that coordinates with 3 seconds to 9 seconds. So we know we're moving to the left between 3 and 9 seconds. Let's take a look at the same question now using a calculator. So when we're talking about finding the zeros for velocity, we're going to put that velocity function in as y1. We're going to set our window according to what they tell us to set it to. So they tell us to look from 0 to 12 seconds. So if you notice, we're going to set our window then from x equals 0 to x equals 12. And then I know that cosine oscillates between 1 and negative 1, and there's no coefficient out front. So I'm just going to go from positive 5 to negative 5. And so here is my cosine function from t equals 0 to t equals 12. And we're looking for the zeros. So this is representing the velocity. Velocity is 0 here and here. So you can see the two zeros here. If you count, this is 3 seconds. This is 4, 5, 6, 7, 8, and this is 9 seconds. So we need moving to the left, which is negative velocity, which is right here. So we must be in that interval. For part B, we're going to do the same thing. We're going to show you how to do it without a calculator and then with a calculator. For part B, it says write but do not evaluate an integral expression that gives a total distance traveled by the particle from time t equals 0 to t equals 6. So total distance traveled means using their absolute value function. So we know that distance is the antiderivative. We have to integrate, in other words, velocity to get position. So, we're going to integrate the velocity function, and we're going to use our absolute value signs to show that we're talking about distance, not displacement. And then we're going to put our lower and our upper bounds here, because it says right here in part B, we don't want the entire interval. We only want from 0 to 6. Okay, so this is just a 1-point question. That's it. You either get it right or wrong. So that would be a no calculator type of question. I would say that you probably could, you probably could integrate this. It's not too bad to integrate by hand, but they're not asking you to, at least not yet. If we change this question to write an expression for the position of the particle, then just a quick caveat here, how position and distance travel are different. Position means we drop the absolute value signs. We want the actual position. It could be positive, it could be negative. And then we have to add the initial condition of where we start. So this would turn into the value of the value -2, because we have a position of -2 there. So this is representing our displacement, and this is representing the initial position. If we look at solving this with a calculator, notice I crossed out write but do not evaluate. since we have a calculator, we can evaluate this. So we're going to look at the function again, and we're going to go from 0 to 6. So we're going to start here, and we're going to end here. So looking at this, there's t equals 0, there's t equals 6. There's the integral expression for the total distance traveled. We know that the total distance is a positive value, which is why we have the absolute values here. So when we look at, I always encourage putting the function into y1 and using your vars key to set up any f-ints or n-derivs. So I'm using my vars key here to get y1. So I'm integrating from 0 to 6 my function y1, and I get 3.8197. So if you notice, that's shading in this red area, but since the absolute values are here, this red area becomes positive, and so it's this total red region, and that total red region has an area of 3.8197, so when we round that, that would be 3.820. Notice we put 3 decimal places on that so that it's in accordance to the free response criteria of part C. We'll go through the no calculator solution first. It says find the acceleration of the particle and tell us if the particle is increasing or decreasing or neither at t equals 4. So if we want the speed, we know, if we want the acceleration, then we know we need to differentiate this. So we know that acceleration is the derivative of velocity. We need a chain rule in here. So the derivative is minus sine pi over 6 times t times the derivative here, which is pi over 6. So rearranging that, we get that. So here's our acceleration. And we want to know what's happening at t equals 4. So when we substitute 4 in, we can see that our acceleration is this much. And I don't really care what the sine of 2 pi over 3 is. This is a solution in itself. College Board might give you this in the solution, but really you can just stop here. You don't have to plug in any values for sines of theta. So here's your answer. We know the answer is negative. So you can just, you don't have to simplify this, and I don't want you to. I don't want you to get it wrong. We just know that the acceleration is negative. All we're being asked for is whether the particle speed is increasing or decreasing. So we know the acceleration is negative. Let's find what's happening with the velocity at 4 seconds. So we're going to plug in 4, cosine of 2 pi over 3. We know 2 pi over 3, if this is the top of the circle and that's the bottom of the circle, 2 pi over 3 is over here on the left-hand side of the circle, so it's also a negative. We're not going to simplify it. We don't need to. We don't need an answer. We just know it's negative. We know it's less than 0. So we have a negative velocity. We have a negative acceleration. Those two signs match. So we know the speed is increasing because they have the same sign. Looking at this from a calculator standpoint, we start in a very similar fashion. We know acceleration is derivative of velocity. And we know we have the velocity here in y1 on our calculator. So we're going to just go ahead and plug in 4 to get our value for our velocity. And then we're going to go ahead and do an n-deriv, a math n-deriv. And we're going to grab y1 and 4, and here is the acceleration. And we notice that the signs are the same. And so if the signs are the same, we must be speeding up. For part D, it says find the position of the particle at time t equals 4. So position, we know, is the integral of the velocity. That'll give us displacement. And then we have to add the initial position on. So that expression looks something like this, where the displacement is the integration of the velocity function. That's how far how far it moves. And then we have to add on the initial position from where it starts to find our final position. So without a calculator, we have to integrate this. So the integral of cosine is sine of pi over 6, and then we have to divide by that. We do a chain rule here. We have to divide by pi over 6. That's kind of our quick way of doing the use of our reverse chain rule. So simplifying this, it looks like 6 over pi times sine pi over 6t. So looking at this, if we do a quick derivative with the chain rule, we'll get back what we started with. We're going to evaluate that from 0 to 4, and then we're going to add the initial position. So plugging in 4 and plugging in 0 looks like this. Evaluating this, we have 6 over pi sine 2 pi over 3 minus 0 plus a negative 2. That's our initial position. We know that because it says t equals 0. So simplifying it just a little bit more, maybe not writing the 0 is really all you have to do. This is a complete answer. Again, if you notice, you don't have to evaluate this trig function. This is the answer. You can keep it at that. Even if it's a calculator question, you can still keep the answer at that if you want to do this by hand. So there's your answer. That's your position when t equals 4. If we look at this using a calculator now, finding the position of the particle, well, all we're going to do is take that expression for final position, which is displacement plus initial position, and we're going to put that into our calculator. So again, I always like to reinforce, put the function in y1 so you can use your vars key. It just goes faster. We're going to go ahead, and if you notice what I type into my calculator here looks a lot like the expression I write on my paper. I just don't put the calculator syntax in there because they don't like that at the College Board. So from 0 to 4, y1 dx minus 2, there's my final position. So go ahead and write down your answer. Again, that's your displacement, that's your initial position. Your final answer is rounded to 3 decimal places, so it's negative 0.346.